Hi everyone, today we'll be looking at the June 2019 statistics paper. In question 1, we've got 3 bags A, B, C, each containing a red marble and some green marbles. Specifically, bag A contains 1 red and 9 green, B it's 1 and 4, and C is 1 and 2 respectively. Now Sasha selects a marble at random from A. If it's a red, he stops. If it's green, he continues by selecting 1 marble from B. If it's again red, he stops. If not, he continues by selecting a marble from C. And we need to draw a tree diagram to represent this information. So I will start by drawing here the first marble drawn. It's from A, so I'm gonna put an A here. So it could be red or it could be green. There's a total of 10 marbles, so 1 of them is red and 9 of them are green. Now, if it's a red, we stop. If it's green, we draw a marble from the second bag B. So it could again be red or green. There is 1 red and 4 green, and this is bag B. And then if it's green, again, we draw from bag C, and it could be red and green with probability 1/3 and 2/3 respectively. So that's the tree diagram. Part B, find the probability that Sasha will select 3 green marbles. So the probability of green, green, green is found by multiplying the probabilities of the branches through which I travel. So the probability of green, green, green will simply be 9/10 times 4/5 times 2/3, and this is equal to 12/25. C, what's the probability that Sasha selects at least 1 marble of each color? Well, at least 1 marble of each color could be green, red, or green, green, red, so that we've got a red and at least a green. So this would be 9/10 times 1/5. That's the green-red scenario, plus green times red. And this is equal to 21/50. Part D, given that Sasha selects a red marble, what is the probability that he selects it from bag B? So we know for sure that we got a red marble, so we're here, here, or here. And what's the probability that we selected this red marble from B, which is this one? So what I have ticked will be my denominator, and the cross here will be my numerator. So this will simply be the 9/10 times 1/5 over the 1/10 plus 9/10 times 1/5 plus 9/10 times 4/5 times 1/3, and this is equal to 9/26. In question 2, we've got a partially completed box plot. Now, an outlier is being defined to be 1.5 interquartile range above Q3 and below Q1. We are being given the 3 lowest temperatures and the highest temperature, and we need to complete the box plot. Now, I will start by actually determining the interquartile range. So Q1 is over here, Q3 is over here. So paying attention to the scale, I can say that the interquartile range will be 26.6, which is the upper quartile, minus 19.4, which is the lower quartile, which is 7.2. And therefore, my limits will be 26.6 plus 1.5 times 7.2. That's 1.5 interquartile ranges above Q3, which is 37.4. And 19.4 minus 1.5 times 7.2, which is 8.6. So this is the lower limit. So if I look at the data being given here, it's obvious that 7.6 and 8.1 are outliers, 32.5 is not, 9.1 is not. We know that outliers are identified with crosses, so 7.6 is here, 8.1 is here, and I draw my whiskers at the last observations which were not outliers, so 9.1 and 32.5. So 9.1 is here, 32.5 is here, and I'll join this together to complete my box plot. That was part A. Part B, using your knowledge of the large dataset, suggest from which month the two outliers are likely to have come, where we're looking at air temperatures in Beijing in 2015. Notice that the two outliers are particularly low temperatures. I'm just gonna state this, so particularly low temperatures. Therefore, it must be October, as it is the month with the coldest temperatures between May and October. Now remember that in the large data set, we've got data from May to October for 2015 and 1987. So we have seen particularly low temperatures. It must be the weather season, it must be the winter season, so it should be October. Now, we're beginning the summary stats for part C and being asked to show that to 3SF the standard deviation is 5.19. So if you look at the formula booklet, we're being given that sigma is SXX over n, square root of that, which is 4,952.906 over 184, which gives an answer of 5.18825, which rounds to 5.19 degrees Celsius as required. I would like to draw your attention here to the fact that if you just went from this calculation to the 5.19, you wouldn't score the mark. You need to quote the answer here. That's why I'm highlighting this. You need to quote the answer to more accuracy to justify the rounding to the printed answer. And then part D, we've got someone who decides to model the air temperatures according to this random variable. We need to calculate the 10th to 90th interpercentile range. Well, let's start by writing out the distribution. T follows normal 22.6, 5.19 squared. What do we mean by the 10th to the 90th interpercentile range? Simply means that we need to find this point here, which I will call P10, and this point here, which I will call P90, so that this region here is 10%, and this region here is also 10%. In other words, I need to find P10 such that the probability of T being less than P10 is 0.10. My calculator can do that straight away. I get P10 to be 15.94874, and the probability of T being less than P90 is 0.90. So P90 turns out to be 29.24901. Notice that by symmetry, the midpoint of these two should be the mean because the normal distribution is symmetric. So you can check that the midpoint of these two numbers is 22.6. Now we haven't finished this part. We need to say that the 10th to 90th interpercentile range will be the difference between these two numbers, will be 29.24901 minus 15.94874, and this is equal to 13.3, and it's in degrees Celsius. Now Simon wants to model another variable using a normal distribution. State two variables that are not suitable to be modeled as a normal distribution, giving reasons for your answer. Now the normal distribution is a continuous distribution and it's symmetric. Anything that is not continuous or anything that is not symmetric will not be suitable to be modeled via a normal approach. So we know that the dataset for Beijing includes wind in Beaufort scale. So this will not be suitable because it's a categorical variable. It comes in classes. So it's a categorical variable, not continuous. And another variable that wouldn't be suitable for the normal distribution would be the rainfall, not because it's not continuous, but because it is not symmetric. There are many days with no rainfall, so it is not symmetric, as there are many days with no rainfalls. Question 3, we've got Barbara who's investigating the relationship between GDP and carbon dioxide emissions. She took a random sample of 24 countries. She obtained R to be 0.446. Stating our hypothesis clearly, test at the 5% level whether we have evidence that the product moment correlation coefficient is greater than 0. So this is a hypothesis test. We will start off as usual by writing out our null hypothesis. Rho is 0. H1 rho is greater than 0. Alpha is 0.05. Once more, let me remind you that you have to use the Greek letter rho. Anything else will lead to a mark being deducted. We have obtained R to be 0.446 with a sample of size 24. So looking at the table of values provided in the formula booklet, we find that the critical value is 0.3438. It makes it really easy to decide on whether we need to reject or not reject. If we just draw this is the critical value. Obviously the critical region is here. What we have just seen is obviously well within the critical region. There it is. So 0.446, and therefore we will simply say that 0.446 is greater than 0.3438. Significant. Reject H0, and we need a conclusion in context to get full marks. So evidence of a positive correlation between GDP per capita. We need to mention the variables. And CO2 emissions. Now, Barbara believes that the nonlinear model will be a better fit, so she codes the data. She took the logarithms of x and y and obtained this model. The PMCC between the coded variables turned out to be 0.882. The question is, how does this value support Barbara's belief? Now, we have to say that the PMCC, the product moment correlation coefficient between log x and log y, is close to 1. Hence, there is a strong linear association between log x and log y, thus supporting Barbaras's belief. Now, before we proceed to the next part of the question, let's look at the PMCC we found here. We found the 0.882. Not only is it close to 1, but it's also greater than the 0.446 we found here. So it is a better fit. So I think it would be better if we just say close to 1 and greater than 0.446. So it's a better model than the original model where we were associating the original variables without any coding. And then part C show that the relationship between y and x can be written in the form y is ax to the n with a and n constants to be found. Well, we start off with the equation we've been provided that c is minus 1.82 plus 0.89 m. And then we know that c is the log of y base 10 and m is the log of x base 10. Now the suspected model is y is ax to the n, so it makes sense to take logs of both sides. I use the product rule of logarithms to write this as log a plus log x to the n, which can be further written as log a base 10 plus n log x base 10. That's log of y base 10 on the left hand side. And if I compare and contrast these two, it's easy to see that the minus 1.82 is the log of a and the 0.89 is the n. So minus 1.82 is log a base 10 and 0.89 is n. This means that 10 to the minus 1.82 is equal to a. So we've got a to be 0.0151 and the model is y is 0.0151, x to the 0.89. We give answers to 3SF. Now n turned out to be 0.89, so I'm just gonna stick to 0.89. In question 4, Magali is studying the mean total cloud cover in octas for Luchers. This is the data obtained for the 184 days from the large data set. And we select a day at random, and what's the probability that it has a daily mean total cloud cover of 6 or greater? Well, 6 or greater is the 52 and the 52 and the 28, so that the answer to part A should simply be 52 plus 52 plus 28 over 184, which gives an answer of 33 over 46, which to 3SF is 0.7174. Now, in part B, we are told that this binomial model is used to model the daily mean total cloud cover. What's the probability of x being greater than or equal to 6? And what's the expected number of days in 194 days with a daily mean total cloud cover of 7? So we've got that x follows a binomial 8, 0.76. And for part I, the probability of x being greater than or equal to 6 is 1 minus the probability of x being less than or equal to 5. My calculator is giving me the probability of x being less than or equal to 5 as 0.2967. So the answer is 0.7033. Now for the II part, the expected number of days in a total of 184 days for which the cloud cover is 7 is simply 184 times the probability of x is equal to 7. This will give me the proportion of days that have a cloud cover of 7, and I multiply by my sample size to turn it into the expected number of days. So this is 184 times the probability, which is provided by my calculator, 0.2811877 ... which is 51.7 days. Note that it's the expected number of days, so it's okay to get a non-integer answer. In C, explain whether or not your answers to part B support the use of Magalis's model, where we can simply compare what we have observed with what we have calculated. They are quite close, so this seems to support the model. And also for 7 days we had 52, that's the observed frequency, and this is the expected frequency, almost identical. So we can certainly claim that the model seems to be valid because 0.7033 is close to the observed probability. Of 0.7174. In addition, 51.7 is close to the observed frequency of 52. And therefore, Magalis's model is supported. Now we had 28 days with a daily mean total cloud cover of 8, and this is the data for the following day. So what was the daily mean total cloud cover for the following day? Find the proportion of these days with the daily mean total cloud cover being 6 or greater. So 5 plus 9 plus 9 over 28. So 5 plus 9 plus 9 over 28, which turns out to be 23 over 28, which is 0.8214. And then for part E, comment on Magalis's model in light of our answer to part D. So this is really asking you to consider the assumptions of the model by Magali and whether these seem to be satisfied. Now, the binomial model has the assumption that the trials are independent and there is a constant probability of success. Now, in this particular case, a trial is a day, so days are independent and cloud cover on each day is independent, and the probability remains the same. So I will start by stating that Magalis's model assumes that cloud cover on any given day is independent of all other days. In other words, this means that me telling you the cloud cover of yesterday or the day before tells you nothing about the cloud cover of tomorrow. So this means that the probability of x being greater than or equal to 6 should be roughly equal to the probability of x being greater than or equal to 6 given that previous day cloud cover was 8. So in other words, being revealed that the previous day cloud cover was 8 tells you nothing about the probability of cloud cover on the next day being 6 or more. Now, since 0.8 to 1,4, which is this part here, obtained from D, is not close to 0.7033, which is the unconditional probability we obtained at the very start of the question, Magalis's model is not valid. So the assumption of independence seems to be violated. In question 5, it's a machine that puts liquid into bottles of perfume. Now, capital D is the amount of liquid and it follows normal distribution with a mean of 25. We know that 15% of the bottles contain less than 24.63 ml, and we need to find K such that the probability we are between 24.63 and K is 0.45. I will start by writing out that we know that D follows normal with mean 25 and standard deviation sigma. We know that the probability of D being less than 24.63 is 0.15. Now, because sigma is unknown, I will have to standardize and move to the standard normal distribution denoted by Z by deducting the mean and dividing by the standard deviation. I use my calculator to obtain that 24.63 minus 25 over sigma is equal to minus 1.0364 ... Now this means that minus 0.37 over sigma is equal to this, and I can solve for sigma, and I find that sigma is 0.35699 ... Sigma was not my final answer here because I need to find the value of K satisfying all of these. I think it's time to draw a bell-shaped curve just to see exactly what's happening. We have been told that the probability were between 24.63 and K is 0.45, so all of this is 0.45, but we also know that the probability of being less than 24.63 is 0.15. So all of this can be nicely summarized into the probability of D being less than K is equal to 0.6 because it's the 15% and the 45%. But now I know the value of sigma, I know mu is 25, so using my calculator, I get K to be 25.09. Part B, we've got a random sample of 200 bottles taken, and using a normal approximation, we need to find the probability that fewer than half of these bottles contain between 24.63 and K ml. So my random variable now will be X, defined to be the number of bottles containing between 24.63 ml and K ml. Now, we know that each bottle will be tested independently and it might or might not contain between 24.63 and K ml. So it's a binomial random variable with with n being 200 and probability of success being 0.45. Now we know that the mean of this binomial random variable is NP, which is 200 times 0.45, which is 90. And the variance is NP1 minus P, which is 200 times 0.45 times 1 minus 0.45, which is 49.5. So Mr. X can be approximated by another random variable, I will call it Y, which follows a normal distribution with mean 90 and a variance 49.5. Now, the question said less than half the bottle, so probability of X less than 100 is the same as the probability of x less than or equal to 99. Well, if I write these statements once in a strict inequality and another time as a relaxed inequality, the midpoint of the two will be the continuity correction I need to apply. So this will be approximately the probability of y less than 99.5. Why is all of this needed? Well, simply because the binomial is a discrete distribution and the normal is a continuous distribution. On one hand, S can take values, integer values only, so it could take a 99, 100, and 101. However, the normal distribution is continuous, so it can take values in between, and I need to take that into account. So the half continuity correction is moving from 100 to 99.5. I then just plug in everything on the calculator, and it's 0.9115. Now the machine is adjusted so that the standard deviation is 0.16 ml. Now Hannah believes that the mean amount is less than 25 ml. She took a random sample of 20 bottles. This gave a sample mean of 24.94. We need to test her belief at the 5% level. So hypothesis test here. We start the usual way. We write H naught mu is 25. Now Hannah suspects, she believes that mu is less than 25. Alpha is 5%. We know that sigma is 0.16. We have a sample of size 20. We obtain a mean of 24.94. Under H naught, so if the null hypothesis is indeed true, X bar will follow normal with mean 25 and variance 0.16 squared over 20. Now, we inherit the direction from the alternative hypothesis, so less than. The probability of X bar being less than 24.94 is equal to 0.04677. This is less than my threshold, my alpha level, the 5%, so it's significant. We reject H naught, which means that we have evidence to support Hannah's belief.